From a Surrey racing circuit built by a wealthy landowner in 1907, Britain learned to fly and kept flying, building aircraft across 8 decades, nearly 19,000 of them making their first flights from the same flat stretch of ground. By the early 1960s, the factory at Weybridge had designed the world's first turboprop airliner, built the VC-10, and was now assembling the TSR-2, a supersonic strike aircraft designed to thread through Soviet air defences at 500 knots, below the radar, in the dark, carrying a nuclear weapon to targets no other aircraft could reach. Then the decisions began. A new government, a balance of payments deficit, a budget that needed saving. On the 6th of April 1965, James Callaghan rose in the House of Commons and cancelled TSR-2 as a line item, £35 million, saved in the current financial year. The test pilot assigned to fly the second prototype heard the news from a pub television. The aircraft was impounded before he could reach it. The replacement ordered in its place was cancelled 3 years later. The factory continued for another 2 decades, then closed in 1988. The runway fell silent. The aircraft sits at Duxford now, white, undercarriage down, intakes open. The factory that built its front half is a museum. This is the story of what was assembled at Weybridge, the knowledge, the craft, the ambition, and what a single budget speech, on a morning when a fuel pump was being changed, chose to do with it. Chapter 1. The concrete that dreamed of flight. The story begins not with an aircraft, but with a bet. In 1906, a wealthy Surrey landowner named Hugh Finch Lock King looked at a flat piece of farmland beside the River Wey at Weybridge and decided to build something that had never existed anywhere on Earth. A racing circuit. Purpose-built, vast enough to have banked corners of reinforced concrete rising 30 feet into the air. Designed by a Royal Engineers colonel named H.C.L. Holden to allow motorcars to run at speeds previously considered suicidal. The project cost Lock King somewhere in the region of £150,000 of his own money. His wife Ethel helped finance it. His neighbours thought him eccentric, possibly unhinged. Brooklands opened in June 1907. It was the world's first purpose-built motor racing circuit, a fact historic England would eventually formalise in its listing. And within months of opening, it had become something its creator never fully anticipated. The banked concrete and the long flat straights weren't just useful for motorcars, they were useful for aeroplanes. The long straight section at the airfield end of the circuit, flat, open, clear of obstacles, was almost exactly what a fragile early flying machine required. So they came. The builders of biplanes, the tinkerers, the ex-cavalry officers who'd decided that horses were yesterday's machine and wanted to understand what came next. By 1910, Brooklands was a racing circuit that also happened to be a flying ground. By 1914, it was clear which of those two identities would outlast the other. Lock King had built himself a track. He had, without knowing it, built the birthplace of British aviation. The first flight at Brooklands. The first test. The first climb away from the Surrey clay. It began with racing cars screaming round banked concrete. It ended, 80 years later, with engineers assembling some of the most technically advanced military aircraft ever attempted by any nation on Earth. Nearly 19,000 aircraft made their first flights from that ground. 19,000. From a circuit built to make motorcars go fast. But the last aircraft assembled there, the one that carries the full weight of this story, never made its first flight at all. Chapter 2. The works that war. Built. Britain went to war in August 1914, and Brooklands immediately understood what it was for. The track had been hosting aviation since 1910, and a small but concentrated community of aircraft builders had grown up inside and around its perimeter. There were sheds, workshops, the improvised infrastructure of a technology finding its footing. When the War Office began looking for industrial capacity to produce military aeroplanes in volume, Brooklands was already half organised for the purpose. The decisive institutional move came in 1915. Vickers Limited, an engineering giant already producing artillery, naval guns, and the structural sinews of British war-making took over the former Itala motorcar factory that sat within the circuit's own footprint. The conversion was rapid. A space that had been manufacturing Italian cars was reorganised for aircraft production within months. Vickers had the engineering discipline, the management systems, the supply chains. The factory had the floor space and the airfield on the doorstep. The first military aircraft rolled out, taxied across the flat ground, and climbed. It did not look, from the outside, like the founding moment of something that would last 70 years. It looked like an expedient arrangement made under pressure of total war. But Vickers would stay at Brooklands for the remainder of the century, and the institutional memory that accumulated inside those buildings, the knowledge of how to build flying machines, the skills passed from engineer to engineer and craftsman to craftsman, would prove to be one of the most durable technical inheritances in British manufacturing history. The aircraft Vickers built during the First World War were wood and canvas, wire-braced, underpowered, terrifyingly vulnerable. The men who flew them died in proportions that their families were not always told the truth about. But the factory kept building, kept refining, kept learning what held together at altitude and what didn't. Every failure was information. Every crash that didn't kill the pilot was data. After the armistice, the urgency evaporated, as it always does, and the aircraft industry contracted sharply. Brooklands contracted with it. But Vickers remained. The factory was smaller, quieter, producing for a peacetime market that barely existed. It didn't matter. The skills stayed. The people stayed. The institutional knowledge, the understanding of what it meant to make an aeroplane properly, from the inside out, stayed embedded in the workforce and the design offices. That patience would matter enormously because the next great expansion was coming. The question was only when. Barnes Wallis arrived at Vickers in 1913, left briefly for the war, and returned. He would stay for the rest of his working life. His name will appear again in this story. It will appear more than once. Chapter 3. The Man Who Thought in Structures. Barnes Neville Wallis was not an obvious factory genius. He was slight, meticulous, soft-spoken, a man who preferred the drawing office to the shop floor, who communicated in precise technical language, and who had a gift, unusual even among engineers, for understanding how forces moved through structures. Not just how a material behaved under load, but how the shape of a thing could be made to carry stress more efficiently, how an airframe could be made lighter by understanding where the weight actually needed to be. He had trained as a marine engineer. He came to aircraft almost sideways, through an interest in rigid airships, and his early career at Vickers had involved the R-100 Demolished, a British attempt at a commercial passenger airship that flew across the Atlantic in 1930. A remarkable engineering achievement before the entire airship program was killed overnight by the destruction of the R-101. Wallis had been right about the R-100. It didn't save the program. It merely meant he'd been right in the middle of a different kind of tragedy before this one. What Wallis brought to Brooklands was a particular kind of structural thinking that crossed the boundary between the technical and the visionary. In 1936, he began working on a problem that had no obvious solution. How do you sink a German battleship when conventional bombs lack the penetrating power to punch through the armoured deck? His answer, the earthquake bomb, or more precisely, the 5-ton tallboy, and then the 10-ton Grand Slam, required understanding not just explosives, but the behaviour of earth and reinforced concrete under shock waves. The Tirpitz. The Bielefeld Viaduct. Bombing raids that changed the strategic calculus of the war, delivered by weapons that Wallis had designed in offices at Brooklands. And before the tallboy, before the earthquake bomb, the bouncing bomb. Operation Chastise, May 1943. 19 Lancasters flying low across the Ruhr. The Möhne Dam breached. The Ada Dam breached. 133 million tons of water released into the valley below. Factories flooded, mines flooded, power stations cut off. The men of 617 Squadron, all, a third of whom did not come home, delivering one of the most technically audacious attacks of the war. The weapon that made it possible, a cylindrical drum of Torpex explosive, precisely engineered to skip across water at a specific speed from a specific height. Developed by a Vickers engineer working in Surrey, who had tested early versions by rolling marbles across a bath and recording where they landed. That man worked at Brooklands. After the war, Wallace went back to thinking ahead. The stratosphere chamber, built at Brooklands in 1946, was a pressurized research facility designed to study flight at very high altitude and very high speed, conditions that no aircraft had yet consistently achieved. It was thinking into a future that didn't exist yet. Wallace was interested in flight at Mach 2, Mach 3, speeds at which the aerodynamic heating of a fuselage became a structural engineering problem of the first order. The chamber sat inside the Brooklands site, humming with compressed air, working through problems that wouldn't be practically relevant for another decade. Nobody told him to stop. Nobody moved him sideways. He worked. It is worth understanding what this means about the place. Brooklands, by the late 1940s, was not simply a factory that manufactured aircraft to specification. It was a place where research of the most fundamental kind was happening in parallel with production. The man who had designed the bouncing bomb was now thinking about hypersonic flight. The people building current aircraft were 3 corridors away from the people thinking about aircraft that wouldn't exist for 20 years. That concentration, of present and future, of craft and imagination, of the specific and the theoretical, was not common. It was, in fact, extraordinarily rare. And it had been assembled over 30 years inside a Surrey airfield that had started as a racing circuit. Chapter 4. Clocking in at the edge of the future. If you were a young man starting an apprenticeship at Vickers in the early 1960s, you'd have walked through gates that opened onto a world with its own internal logic. The site wasn't one building. It was a complex of hangars, design offices, test rigs, and machine shops connected by internal roads, with the airfield runway running through the middle of it. A strip of concrete that bisected the factory site like a seam. The smell was particular. Machine oil, definitely. The specific sharpness of aluminium being cut. A smell with a metallic edge that got into the back of the throat. In the bonding shops, there were adhesives with a solvent quality, not unpleasant but unmistakable. The kind of smell that lodged in the memory and came back decades later without warning. Deeper in the works, the sound, the steady rhythm of rivet guns, the high whine of precision drilling machinery working through aluminium alloy, the compressed air hiss that meant something was being fitted or released, the baseline hum of a large building being continuously used. Terry Rawkins began his apprenticeship at Brooklands in 1962. He was assigned to the instrument workshop, the room where the delicate, critical measuring equipment that the aircraft systems depended on was calibrated, tested, and maintained. Down the corridor and through 2 sets of doors was Barnes Wallace's R&D department. Not a legend. A man. Slightly built, working at a desk, with a mind that was still in his 70s, running ahead of almost everyone in British aerospace. Rawkins was 18. He joined a factory where the man who'd breached the Ruhr dams was still coming in every morning. The apprenticeship system was the factory's method of reproducing itself. Young men entered not knowing what metal fatigue was, or how a control surface was rigged, and emerged 4 years later as craftsmen who understood the tolerances required to keep a human being alive at 40,000 feet. The knowledge wasn't written down in a way that could simply be transferred. It existed in the hands and judgment of experienced workers, and it moved from generation to generation through proximity and practice. An apprentice didn't just learn what to do. He learned why it mattered. He learned what happened when it went wrong. By the early 1960s, Vickers had been acquired into the British Aircraft Corporation, a government-engineered merger of British aviation's surviving major manufacturers, and the works at Brooklands now sat within a larger industrial structure. But the culture of the site was still continuous with what it had always been. The same design office sensibility. The same conviction that the problems worth working on were the ones that hadn't been solved yet. The VC-10I Aim, a long-haul jet airliner of exceptional elegance, designed at Weybridge to operate from short runways in hot climates, was in production. Its prototype had made its first flight in June 1962, piloted by Jock Bryce and Brian Trubshaw, lifting off from Brooklands' own runway and climbing into Surrey sky. BOAC put the VC-10 into service in 1964. To fly in one was to fly in something made with a degree of care that wasn't always commercially rational. It was faster than most jets then operating, quieter at the cabin. Its 4 rear-mounted engines kept the wing clean and the passenger experience smooth. Pilots loved it. Those who'd flown in one and in the competing Boeing 707 tended to have a view about which was the better aircraft. 14,000 people worked at Brooklands at its peak. 14,000. The site that Hugh Lock-King had built for racing cars had become, within 50 years, one of the largest aerospace manufacturing complexes in Europe. The roads around Weybridge were shaped by it. The pubs were full of it at the end of a Friday shift. Families traced their connection to the factory across 3 generations: grandfather who'd made Spitfires, father who'd built Viscounts, son who'd just started on the shop floor. Meanwhile, in the drawing offices, the next aircraft was taking shape on paper. It would be unlike anything that had come before. Chapter 5. The airliner years and what came after them. The Vickers. Viscount entered service in 1950. It was the world's first turboprop airliner to carry fare-paying passengers, and it sold, ultimately, to airlines across 30 countries. 445 were built. It made Vickers the dominant British airliner manufacturer of its decade, and it was followed by the Vanguard and then the VC-10, a lineage of civil aviation that proceeded from the same design offices, the same Weybridge drawing boards, across a working lifetime. A man who started as a draftsman at Vickers in 1950 could look up in 1964 and see an aircraft he'd personally contributed to climbing out of Heathrow on its way to Lagos. That continuity, the sense that the work was building towards something, that each aircraft was a development of the last, that the knowledge accumulating in the factory had somewhere to go, was not universal in British industry. At Brooklands, it was the structure of working life. But the civil airliner business was becoming a harder place to make a living. The Americans had the Boeing 707 and the Douglas DC-8, both backed by the enormous development costs that had been paid for by US Air Force procurement, taxpayer-funded research that then transferred into commercial products. British manufacturers were competing in a market where the opposition had a subsidy they could never match. The VC-10 was arguably a better aircraft than the 707. It didn't matter enough. The economics told a different story. The future of Brooklands, it was becoming clear by the early 1960s, did not lie entirely with civil airliners. It lay with the RAF. And the RAF wanted something that, as far as anyone could tell, was impossible. Chapter 6. A requirement that wanted everything. The RAF's strategic problem, in the mid-1950s, was real and rapidly worsening. The English Electric Canberra, a jet bomber that had entered service in 1951 and was a fine aircraft for its time, was aging into obsolescence faster than anyone had anticipated, because the Soviet Union's air defense systems were advancing faster than anyone had anticipated. Surface-to-air missiles, radar coverage, fighter interceptors capable of reaching altitude quickly enough to threaten a bomber before it reached its target. The answer, the RAF concluded, was to get below the radar, to fly so low and so fast that the defences had no time to respond. And while you were there, low, fast, threading through terrain, you needed to be able to locate a precise target, strike it accurately with a nuclear or conventional weapon, and then photograph the results for later assessment. All in one aircraft. All by the same crew. In October 1957, the Ministry of Supply issued Operational Requirement GOR.339. Its demands were, by any measure, extraordinary. The aircraft had to fly at supersonic speeds at low level, below the radar, down in the turbulence where the air is thick and the ride is violent. It had to navigate with accuracy over hundreds of miles of featureless terrain without reference to ground installations. It had to find and strike a target at night or in cloud. It had to take reconnaissance photographs on the same sortie. It had to be able to operate from rough, improvised airstrips if conventional runways were destroyed or inaccessible. And it had to carry a nuclear weapon. Nothing in the world could do all of this. Nothing had ever been designed to. On January 1st, 1959, the government announced that a design had been selected. The successful proposal had come from a newly formed consortium, English Electric, working with Vickers Armstrongs. The aircraft would be built across multiple sites. The forward fuselage and wings would be assembled at the former Vickers factory at Weybridge. The rear fuselage would be built at the English Electric facility at Samlesbury in Lancashire. The two halves would be mated, tested and readied for flight. They called it TSR-2. Tactical Strike and Reconnaissance Mark II. A designation that told you almost nothing about what it actually was. What it actually was, the most technically ambitious aircraft that Britain, or arguably anyone, had ever attempted to build. Chapter 7. Weybridge builds the front half. The aircraft that came together at Weybridge from 1961 onwards was, by any honest measure, a different order of machine from anything that had preceded it. It had to fly at 500 knots at very low level, faster than most fighters of the era could manage in the same conditions, down where the air is dense and turbulent and the ground arrives before you have time to think. It carried a terrain-following radar system designed to allow it to thread through valleys automatically, the aircraft's nose rising and falling in response to what the ground ahead was doing. Nobody had successfully integrated such a system into an operational aircraft before. The navigation suite was intended to deliver accuracy over long overland flights that current technology couldn't reliably achieve. The two Olympus engines developed by Bristol Siddeley, each producing more thrust than anything previously fitted to a British combat aircraft, were being pushed toward performance levels that required solving engineering problems that hadn't yet been fully defined when the contract was signed. It was not one difficult thing. It was 15 difficult things, all of which needed to work simultaneously, and most of which had never been done before. The production arrangement meant that the workers at Weybridge were building the front half of an aircraft whose rear half was being built by different people, in a different county, to tolerances tight enough that the two sections could be mated at final assembly. This required a level of dimensional control, a precision in measurement and manufacture, that was at the absolute edge of what the factory's tooling could achieve. The assembly jigs, enormous steel structures precisely engineered to hold the airframe components in exact geometric relationship to each other while they were joined. The jigs were not incidental to the process. They were the process. Without them, TSR-2 could not be built. Sir George Edwards was by this point the dominant figure at Vickers Aviation operation and then at British Aircraft Corporation when the government-engineered merger of 1960 brought Vickers, English Electric and Bristol Aircraft together under a single corporate umbrella. Edwards was a Vickers man to his marrow, a draftsman who'd come up through the technical side, who understood what the factory could do and what it couldn't, and who had the engineer's characteristic impatience with people who made decisions without understanding the engineering. The merger had been pushed hard by the Minister of Aviation, Duncan Sandys, who had concluded that the British aviation industry was too fragmented to survive. He wasn't wrong. But the merger was turbulent. The question of which company would lead the TSR-2 program had been bitter, and Edwards found himself managing an industrial organisation that had been assembled by political pressure rather than natural evolution. 9 development aircraft were on order, serial numbers XR219 through XR227. XR219 each tsar, the first prototype, Ijdig Graum, was assembled, completed and moved to the test airfield at Boscombe Down in Wiltshire. XR220 was being readied at Weybridge. Both had been ordered under the contract that British Aircraft Corporation had signed with the Ministry of Aviation. Both carried the assembled knowledge of the Brooklands factory, its jigs, its gauging, its decades of aircraft building discipline, in every riveted joint and machined fitting. In September 1964, XR-219 flew for the first time. Roland Beaumont, English Electric's chief test pilot, was at the controls. The aircraft accelerated down the Boscombe runway and became airborne. It climbed, it handled, it flew. In the control room, men who had spent 5 years solving problems that had no textbook solution stood and watched. What nobody in that room could see, what the instrument readings and the clean first flight concealed, was the decision that was already being assembled in Whitehall. Chapter 8. Fuel Pump Cabinet Budget Speech. Harold Wilson won the October 1964 general election by 4 seats. 4 seats. A majority so narrow it could barely breathe. His Chancellor of the Exchequer was James Callaghan. His Minister of Aviation was Roy Jenkins. His government had inherited an economy running a significant balance of payments deficit. And in those first months, the word that appeared most frequently in cabinet discussions was a single syllable: cuts. The TSR-2 programme had already cost £125 million. That was a figure from which there was no recovery, no return, money spent, gone, converted into airframes and jigs and engineering knowledge that existed nowhere else. The question before the Cabinet was not whether that money was worth spending. It had been spent. The question was whether to continue. The continuation costs were disputed, contested, and subject to optimistic interpretation by the contractors. The Ministry of Aviation's own estimates suggested the programme would run to between £750 million and £1 billion before the aircraft entered service. The contractor estimates were lower. Both sides knew that large novel defence programmes almost always cost more than any estimate, however pessimistic, and almost always take longer. Both sides knew the other knew this. Dennis Healey, Secretary of State for Defence, had been examining the programme with an economist's scepticism. He had been told what the aircraft could do. He had also been told what it would cost. He was a former soldier and a former Don, a man of aggressive intelligence who had little patience for the kind of institutional self-interest that tends to inflate specifications and depress cost estimates. He was not persuaded. The alternative being offered was the General Dynamics F-111, an American swing-wing strike aircraft. It was cheaper, at least in the estimates being circulated. It was available sooner. The United States was offering it on terms that appeared, on the numbers as presented, to represent a rational saving. Whether those numbers were as reliable as the terms suggested would become, later, a question of some relevance. On 1st April 1965, Harold Wilson's cabinet voted unanimously to cancel TSR-2. The vote was unanimous. In Weybridge, in the design offices and on the shop floor, nobody knew. There had been rumours, there had been anxiety, there had been the low-level dread of people who follow these things and know that project cancellations have a smell. But nothing had been announced. Work continued. At Boscombe Down, Wing Commander James Dell, Jimmy Dell, was preparing for XR-220's first flight. He was the test pilot assigned to the second prototype. The ground runs had been completed. The aircraft was ready. The scheduled first flight was imminent. On the morning of the 6th of April, a fueling problem was discovered, a faulty fuel pump requiring replacement before the flight could proceed. A minor delay, the kind of thing that happens routinely in flight testing. Dell went to wait it out in a local pub, as test pilots do, between technical hold-ups. He heard the news from the television. James Callaghan was on his feet in the House of Commons, delivering his budget speech. In a passage dealing with defence expenditure, he announced, as a line item between other economies, the cancellation of the TSR-2 programme, the saving £35 million in the current financial year. Dell set down whatever he was holding and tried to get back to the aircraft. By the time he arrived, it had already been impounded. Its certificate of airworthiness had been withdrawn. The aircraft that had been 24 hours from flight was now government property, in a state of administrative suspension, its future depending on decisions that were going to be made by people who had never sat in its cockpit and would never now have reason to. In Weybridge, men who had spent 5 years building the front half of a machine that had never been explained to the country, never been photographed in flight, never been shown to do the thing it was designed to do, those men heard the news and tried to understand what it meant for them, for their factory, for the 2 decades of accumulated knowledge that had produced the aircraft now sitting, impounded on a Wiltshire airfield. Christopher Soames rose in the Commons on the 13th of April to move a motion deploring the cancellation. He spoke of grave effects on the British aircraft industry. He questioned the method of announcement, the budget speech, no warning, no consultation with the industry or with the RAF officers whose operational future depended on what came next. He was not wrong about any of it. The government had its majority, even the thin one. The motion failed. Roy Jenkins, in a subsequent written answer, attempted to frame the financial logic. The terminal charges, the costs of cancellation, the outstanding contracted commitments, would not exceed £70 million, he said, in addition to the £125 million already spent. So, the total cost of the programme, cancelled mid-development, would be in the region of £195 million. The aircraft it was cancelled in favour of, the F111, was being acquired at a cost that the government described as significantly lower. The F111 contract for the RAF was cancelled in January 1968. The saving announced in Callaghan's budget speech, the £35 million that had justified the overnight impoundment of an aircraft 24 hours from its first flight. That saving was never realised. Britain spent the money. It spent it on a programme that was also cancelled. And the RAF flew without a supersonic low-level strike aircraft for the next decade, until the Seppercat Jaguar entered service in 1974, an aircraft capable of some, but not all, of what TSR-2 had been designed to do. Built in collaboration with France, carrying American-designed weapons, operated at lower performance than the aircraft it was meant to replace. Jimmy Dell never flew XR220. Nobody did. Chapter 9. The argument over the jigs. What happened next to the aircraft, to the tooling, to the engineering knowledge that had been assembled at Weybridge across 5 years? That question became, within a remarkably short time, a matter of genuine historical confusion. The popular account, the one that circulated in aviation circles, in the letters pages of specialist magazines, in the retrospective analyses that began appearing within a decade, held that the destruction had been total and deliberate, that the assembly jigs at Weybridge had been broken up, that technical drawings and blueprints had been destroyed, that the half-built aircraft had been cut with blowtorches to prevent any future government from resurrecting the programme, that it had not merely been cancelled, but eliminated, erased, so that the decision could never be revisited. The emotional logic of this account is powerful. It would make sense as an act of political will to ensure that the aircraft could not be reconstructed, that any future administration attracted by the idea of reviving TSR-2 would face not merely bureaucratic obstacles, but physical impossibility. A cancelled contract can be reinstated. A destroyed jig cannot be reconstructed overnight. But the historical record, when examined carefully, tells a more complicated story. In Parliament, on the 1st of February 1967, less than 2 years after the cancellation, the question was put directly to John Stonehouse, then Minister of Aviation. Was it true, an MP asked, that the prototype aircraft and the manufacturing jigs had been required to be destroyed as a condition of the cancellation compensation? Stonehouse answered, "No, sir." He added that the questioner was under a misapprehension. "There are 5 aircraft," he said. 1 had been sent to Cranfield College of Aeronautics for instructional use. 4 remained in existence for ground research purposes. 5 aircraft. Intact. 2 years after the cancellation that was supposed to have eliminated the programme from possibility. And yet the record beyond that Hansard exchange becomes murkier. The tooling, the assembly jigs, the manufacturing fixtures, the dimensional gauges, does appear to have been disposed of, though the precise sequence and the specific authority under which this happened is not documented in the sources available. It is one thing to preserve an airframe as a teaching exhibit. It is another to maintain an industrial manufacturing capability that has no program to serve and costs money to store. The jigs were enormous, specialized, expensive to house, and useless without a contract to build the aircraft they were designed for. Their fate, scrapping, disposal, gradual physical dismantlement, may have followed from straightforward administrative logic rather than from a specific destruction order. The distinction matters, because a deliberate political decision to destroy the manufacturing capability, to ensure the aircraft could never be revived, is a different kind of act from the ordinary institutional entropy that overtakes cancelled programs. Both result in the same physical outcome, an aircraft that cannot be rebuilt. But one is a policy of erasure, and the other is the slow dissolution of an industrial system that has no purpose anymore. XR219, outclassed, the only TSR2 to actually fly, was delivered to the Army Proof and Experimental Establishment at Weybridge in Essex. It was used for vulnerability and lethality trials, military testing of what happens to an airframe when weapons of various kinds are fired at it. It was eventually scrapped in 1982, 17 years after the cancellation, reduced to structural data. XR222, an uncompleted airframe, was lent to Cranfield for postgraduate teaching, as Stonehouse had described. It was later transferred to the Imperial War Museum at Duxford in 1977, where it arrived in March 1978 and was eventually restored to a state that allows visitors to stand beside it and understand, physically, what the scale of the thing actually was. It is large, larger than photographs suggest. The intake geometry, the wing plan form, the undercarriage designed for rough field operations. All of it speaks of an aircraft built around operational requirements that were never compromised. In the hangars at Brooklands, the workers who had built the front half of XR220, who had spent 5 years inside those assembly jigs, mating the forward fuselage to the wing carry-through structure, rigging the control surfaces, fitting the avionics that would have allowed the aircraft to navigate by night through European terrain, those men now had no program. The factory had Concorde work and other military contracts and would survive for 2 more decades. But the thing they had been building toward, the aircraft that was supposed to represent British aerospace at the full extent of its capability, was gone. Chapter 10. The Replacement. That also died. Britain needed a supersonic strike aircraft. The RAF had been structured around the assumption that TSR-2 would enter service. The cancellation did not remove the requirement. It merely removed the means of meeting it. The F-111I, the American swing-wing strike aircraft that the Wilson government had pointed to as the cheaper, sooner alternative each-day, was ordered in 1965. The unit cost, as the negotiations developed, rose. The delivery dates slipped. By 1967, with Britain in the middle of the sterling crisis that would eventually force the devaluation of November of that year, Dennis Healey's defence budget was under pressure that made the original TSR-2 arguments look modest. The F-111 order, Heinz, 50 aircraft for the RAF, was cancelled in January 1968 as part of the post-devaluation cuts that also ended Britain's military presence east of Suez. Roy Jenkins, by this point Chancellor of the Exchequer, had the task of announcing what had happened. The government had cancelled TSR-2 on the basis that the F-111 was cheaper. It had now cancelled the F-111 as well. The RAF's supersonic low-level strike requirement, the requirement that had been specified in October 1957, that had consumed 5 years of the finest engineering talent in Britain, that had produced an aircraft of extraordinary capability, was going to be met by the Anglo-French Jaguar, a design of more modest ambition, built in collaboration because neither Britain nor France could afford the full cost alone. The gap in British air power was filled, eventually, by the MRCA, the multi-role combat aircraft that would become the Panavia Tornado, a collaborative programme involving Britain, Germany and Italy. The Tornado entered service with the RAF in 1980. It was a capable aircraft. It was the child of international compromise in ways that TSR-2 was not. It was built at Warton in Lancashire rather than at Weybridge in Surrey. Weybridge continued producing Concorde parts. The aircraft was a joint British-French programme with some manufacture at Filton in Bristol and some at Weybridge. Military contracts. The site employed through the 1970s a workforce that was smaller than its peak but still substantial. There were strikes, the factory was a union shop with strong representation, and the industrial tensions of the 1970s reached Weybridge as they reached everywhere. In 1977, a wing spar for a Concorde was being worked on at Weybridge when a worker noticed a crack in a structural member. The significance of this was potentially enormous. Concorde was already in service with Air France and British Airways, and a structural problem in one of its major components was not a minor administrative matter. The investigation that followed was meticulous, as it had to be, and it was resolved. But it is a small illustration of what aerospace manufacturing actually is. Not a production line making identical units to a known specification, but a continuous technical investigation into whether the thing you've made will keep human beings alive under the conditions they'll actually encounter. That culture of investigation, the refusal to be satisfied with close enough, the institutional insistence on understanding what you'd built and why it would hold, was the deepest inheritance of the Brooklands site. It had produced the bouncing bomb. It had produced the VC-10. It had produced, briefly and brilliantly, the most technically ambitious strike aircraft ever attempted by any nation. The Brooklands factory built its last aircraft in 1988. British Aerospace. The company that had absorbed BAC in the late 1970s nationalisation announced that the Weybridge site was no longer commercially viable. The final closure came at the end of that year. The gates closed. The workforce dispersed. The runway where 19,000 aircraft had made their first flights fell quiet. Chapter 11. What the museum keeps alive. The Brooklands Museum. Trust was established in 1987, the year before the factory closed. Sir Peter Masefield, one of British aviation's most distinguished figures, became its first chairman. Morag Barton became its director. The decision to create the museum before the factory had finished operating was itself a recognition of what was being lost, an understanding that the site's significance was historical as well as current, and that some effort had to be made to preserve what could be preserved. The Barnes-Wallis Stratosphere Chamber still stands on the site. The chamber where, in 1946, Wallis had begun thinking about flight at speeds and altitudes that existing aircraft couldn't reach, that structure survived the closure and is now interpreted as part of the museum's account of Brooklands' post-war research history. You can stand beside it and understand, in a way that an archival document cannot convey, the physical scale of the ambition it represented. The Brooklands Museum holds a VC-10. It holds other aircraft from the Weybridge lineage, the Viscount, the Vanguard, the long succession of things that were designed at those drawing boards and built at those assembly jigs. It holds the institutional memory of nearly 80 years of continuous aircraft manufacturing. And it works, in the way that good industrial museums work, to make that memory accessible rather than simply stored. What the museum cannot hold, what no museum can hold, is the living knowledge. The understanding that passed from craftsman to apprentice over 40 years of production. The specific embodied skill of a worker who had spent a career inside those jigs, who knew from the resistance in his hands when a rivet wasn't quite right, who could hear from the tone of a drill whether the alloy was behaving as expected. That knowledge was not written down in any form that survives. It was in the hands of people who grew old after 1988 and are now largely gone. At Duxford, XR222 sits in a hangar. It is painted white. Its undercarriage is down. Its intakes gape. The airframe that was never completed, never flown, never used for anything except teaching aeronautical engineering students. It sits in the light and dark of a Cambridgeshire hangar and allows people to stand beside it and simply look. It is large. That is the first thing you understand. Larger than the photographs suggest. larger than the scale drawings prepare you for. The forward fuselage that was built at Weybridge rises above head height. The intake design, optimized for supersonic performance at low level, is a piece of three-dimensional engineering of genuine elegance. The undercarriage legs are massively over-engineered for rough field operation, designed to absorb the impacts of landing on a strip of unprepared ground, to allow the RAF to operate from airfields that had been bombed or damaged or simply never been finished. It was built to survive in conditions that would destroy ordinary aircraft. The irony sits there without needing to be named. Jimmy Dell never flew it. Nobody flew it. On the morning of the 6th of April 1965, a test pilot sitting in a pub in Wiltshire heard a budget speech on the television, and the aircraft that had been 24 hours from its first flight spent the next 13 years as a teaching exhibit before ending up in a museum in Cambridgeshire. Somewhere in the Weybridge records, in the invoices and the jig drawings and the inspection reports and the test schedules, there are the names of the people who built the front half, who measured and riveted and gauged and tested, who came through those gates every morning for 5 years and worked on the aircraft that would change British air power, and then heard it cancelled in a budget speech, and then came through those gates the next morning anyway, because there was still work to do and wages to earn and skills that didn't stop mattering just because the programme had. They didn't make the decision. They built what they were asked to build to a standard that asked everything of them, and they did it. The aircraft sits at Duxford, and the factory that built its front half is a museum, and the runway where it was supposed to take off from the runway at Brooklands that carried 19,000 aircraft into their first flight. That runway is silent now, embedded in the museum site, its purpose remembered rather than practiced. What was built at Weybridge was not just a machine. It was a demonstration of what Britain could do when it brought everything it had learned into one project. The factories, the universities, the research chambers, the accumulated knowledge of 50 years of aircraft building, all of it concentrated between 1959 and 1965 into an aircraft that was faster, more capable, and more technically advanced than anything else in the world. It was cancelled in a budget speech. The jigs were gone in time. The blueprints are somewhere in the archive, or they aren't. And the aircraft sits in the light, white, undercarriage down, intakes open, waiting. In the way that beautiful things wait, for whoever comes to stand beside it and understand what it cost.